Good afternoon, everyone. I am Priya Natarajan. I'm a faculty member in the departments of astronomy and physics at Yale, and also the current director of the Franke program in science and the humanities. As you all know, we have been running this wonderful Inference project talk series. And today we have convened for the post-talk discussion and conversation led by Professor Zena Tavares. And he will be engaging with, of course, telling us a lot about his own work and his perspective, and engaging with the most recent colloquium that we had last week, given by Kyle Cranmer. And Kyle's talk was titled Causality at the Intersection of Simulation, Inference, Science, and Learning. Before I dive into telling you a little bit more about Zena, I would like to start out by recognizing Mr. and Mrs. Richard and Barbara Franke for their generosity and their support of this program and many other interdisciplinary activities at Yale. And just wanted to remind all of you in the room that we are recording this event, and therefore all participants will have their videos muted for the duration of the talk. And as per usual, questions may be submitted at any time in the Q&A feature, and that we will get to them. So as you all saw last Wednesday, Kyle gave us a sort of a wonderful overview of the role of inference in sort of model building, be it simulations, dealing with data, large amounts of data from, for example, the Large Hadron Collider. And he showed us how we actually do science and how we actually learn by making causal inferences from events that are detected, for example. And so today we are going to hear a fresh perspective from a slightly different disciplinary vantage point, which has been our goal with these talks and the discussion series. So for those of you who may not yet have seen Kyle's talk, the recording will be available shortly. And let me just to inform where Kyle was coming from, let me give you his brief biography. So he's currently a professor of physics and data science at New York University and a visiting scientist at Meta AI. In July, he will become the director for the American Family Insurance Data Science Institute at the University of Wisconsin-Madison. And so his work is really about frameworks that he's developed for collaborative statistical modeling and was extensively used in the discovery of the Higgs boson in 2012 with the two separate experiments that independently made this discovery. And his current interests are sort of at the intersection of physics, statistics, and machine learning. Okay, and for our speaker today, Professor Zena Tavares. Zena Tavares is an associate research scientist in both the Data Science Institute and the Zuckerman Mind-Brain Behavior Institute. He is the first joint hire between two university-level institutes at Columbia. In addition to his Columbia affiliation, he's also the co-founder of BASIS, a new applied AI research nonprofit organization that aims to develop universal reasoning systems and apply them to help solve hard scientific and societal problems. So it shows you the bent that Zena has in terms of application and domains of application that do step out into societal problems. And so his research aims to understand how humans reason. That is how they come to derive knowledge from observing and interacting with the world. He also constructs computational and statistical tools to help advance his work on causal reasoning, probabilistic programming, and other related areas. Prior to joining Columbia, he was at MIT, where he received a PhD in cognitive science and statistics and was a postdoctoral researcher in the computer science artificial intelligence lab, CSAIL. Zena's work has received enormous recognition, including an International Fulbright Science and Technology Award, many other accolades for his papers and his work. I'm not going to hog any more time, and I would like to invite Zena to please take the floor. And just want to say a thank you to both of you for speaking to us today. We are absolutely delighted.
Awesome, thank you. So thanks for the introduction, Priya, and I'm pretty excited to be here, and I'm looking forward to the discussion. So let me just try to share my screen. Great, so the title of my talk is Universal Reasoning Systems, Beyond the Frontier of Simulation-Based Inference. And so this is a kind of a riff of Kyle's paper, a fantastic paper, which is the frontiers of simulation-based inference. And so the general theme of my talk is going to be thinking about what is the current status of kind of simulation-based inference, and what do I think is a few steps into the future, and how can we get there? But this will be, in the spirit of Kyle's talk, very high level and hopefully pretty short, so we can spend most of the time in the discussion. So as Priya said, Kyle does hard and difficult science, investigating the nature of the universe. My goals are, in comparison, a little bit more pedestrian, a little bit more grounded on Earth. And so I'm interested in how can we build machines that can reason a little bit better than the current machines? And in particular, how can we build machines that are somewhat more human-like in their ability to learn and reason about the world? And so here are just some kind of common sense questions which a human might be able to answer. So looking at this picture, you might say, well, the driver's drunkenness likely caused this crash. Or, if you had a weatherman give you some report, you might say, well, that's implausible. Or if you're an epidemiologist, you might be investigating some mutation and say, well, this is really going to lead to some large-scale societal, shutdowns or implications. And so how can we build machines that can do this kind of reasoning? Right now, I believe there's no machines that can really do this degree of general and flexible inference. And so that's kind of my high-level goal. And so the basic foundation upon which I work is the idea that humans, and presumably many other animals too, have mental models about how the world works. And so here in this illustration, the idea is that I, as a human, have some model about the outside physical world, and so I can predict what's going to happen. And this is a really powerful thing to be able to do, because it means that I can imagine how the world is going to unfold without the world actually unfolding in that particular way. And that's a very kind of life-preserving faculty to have. It doesn't necessarily need to be about physical things in the world. I can also reason about other agents, think about what you're thinking, thinking about what I'm thinking recursively, up to some depth. And so there's a variety of different kinds of phenomena in the world. And the basic premise of this approach is humans, they have mental models, and they use these models to imagine how the world would unfold in various different ways. And so my goal is to build universal reasoning systems, and we can get in a discussion if that's a meaningful concept. But I think there are basically three fundamental pillars that we need to think about, at least three. One is the notion of knowledge representations. And again, building off Kyle's talk, some of the most exciting work is simulation-based models as representation of knowledge. The second pillar is different kinds and modes of reasoning, different kinds of questions that we might be able to ask. And the third is different algorithms for inference. And this is more the computational perspective. And so what I want to do in this brief talk is to look at these different aspects, and in each kind, think about one aspect of where we are right now and another aspect of where we might be in the future. Okay, so thinking about modes of reasoning. And so this is a slide from Kyle's talk, and he points to kind of Bayesian inference as this principal foundation. And so what is the premise behind Bayesian inference? Well, the basic idea is that you have some data, you have some theory or some model, and given these two pieces of information, I can update using Bayes' theorem to derive what should I believe now conditional on the evidence. More generally, I think of Bayesian inference as a paradigm for logical inference. And so this idea has a long kind of philosophical foundation. But basically, you have models, you introduce new data, and you revise your models based on evidence. And so one of the questions which I want to get into is how general can we think about this paradigm of Bayesian inference? Currently, the paradigms in which we're doing Bayesian inference, I'll argue, are a lot more constrained than the most general paradigm. And a large part of what I want to do is think about what are the ways in which we are to extend the notion of Bayesian inference to account for different kinds of knowledge and different kinds of information about how the world works. And so let me just give you an example of what I mean here. So another kind of inference is less of the kind that Carl spoke about last week, and more the kind of logical reasoning that we do every day. And this could be, individual common sense reasoning, all the way up to kind of the scientific discoveries, some of which are the most important discoveries in the universe, in the world to this point. So let me just give you an example. So here's Galileo, and I'm sure many of you know Galileo. And Galileo is famous for several things, but he's particularly famous for discovering the nature of the moon. And so Galileo, in the 16th century, he looked up at the moon and he came to this conclusion. He said the boundary which divides the part in the shadow from the shining part does not extend continuously in an ellipse, as would happen to be the case if it was, the boundary which divides the part in the shadow from the shining part does not extend continuously in an ellipse, as would happen in the case of a perfectly spherical body, but it is marked out by an irregular, uneven, and very wavy line. So what Galileo is saying here is that if you look at the moon, as we will do in the next slide, you can see this wavy line between the light part and the dark part. And for all of us, this is an obvious thing, but at the time, people thought that the moon was this perfect sphere. They thought it was this perfectly spherical body, but Galileo looked up at the moon and he said, well, it's not. But it wasn't sufficient for him to just say it's not perfectly smooth. He had to convince his audience. And so his argument basically goes, well, if it was a perfect sphere, the line which connects the light part to the dark part would be a perfectly smooth ellipse, but it's not. And therefore, the moon is not perfectly spherical. So this kind of argument, which is almost like a proof by contradiction, if you've done some mathematics, is very common in everyday reasoning. And it's a very important style of reasoning because it led to a revolution in how we think about the world. And so how can we build machines that can do this kind of logical reasoning? But at the same time, it's not purely logical reasoning because, what are the axioms here? It's not very clear. Is there some kind of formal mathematical basis? So it's this weird kind of mixture between logical reasoning and the messy real world. And so if you think about, what this looks like in a slightly more formal sense, we have some proposition S, which is that the moon is a perfect sphere, some proposition E, that the terminator, which is the divider between the light and the dark side, is an ellipse. And then we construct this kind of argument. Assume that it's true, assume S is true, as in assume that the moon is a perfect sphere, then the terminator is ellipse is also true, but it is not true, and therefore our axiom is false. And so one of the things that we've been looking at recently is, can we build machines that can do this kind of reasoning with kind of real world data? And this is very much just the idea stage. And this is in some sense I'm using this kind of talk as an excuse to think about things which are very speculative. But our goal is to construct something like a proof tree. So you may not be familiar with this notation, but this is how people construct these formal arguments in mathematics. But instead of a kind of a normal mathematical logical proof, we combine that with a generative model. And so on the one hand, we have this formal logical deductive tree. On the other hand, all of the instances, all of the elements, all of the kind of the variables which constitute this logical tree are themselves variables in kind of the kind of generative models that Carl spoke about last week. And this is important because it's not just sufficient to just make this kind of logical argument. I have to connect it to all of my perceptual vision system. I have to actually look at the moon and infer its shape. I have to actually use my visual system. And so what we're trying to do here in this very early stage is try to bridge this gap between logical deductive reasoning and kind of the more generative style kind of Bayesian inference that we're more familiar with. Okay, so I'm just going to move on quickly. So going to algorithms for inference. And so Carl had this has this slide, and he's talking about what is the kind of the state of the art in inference methods. And I think I agree with Carl that one of the most exciting areas here is algorithms which combine neural components with kind of old-fashioned statistical components to get the best of both worlds. And in particular, you can have kind of neural models, neural surrogate models of a kind of a hard to compute conventional model, or you can have a surrogate model of a summary statistic. And there's this really expanding and exploding field of combinations of neural models and kind of more conventional statistical models. And just to go back a little bit, one of the kind of the key ideas behind this approach, which is in Carl's paper, is the idea of automatic differentiation. So there's many kind of values at which you would like to compute. In particular, the kind of the gradient with respect to many different terms, for example, the likelihood, both in a neural model or in a conventional model. But underlying all that is a technology called automatic differentiation. And that's what allows you to get gradients out of a very complicated model that you can't do by hand. And so if you think about what kind of thing is automatic differentiation, well, you can understand it from the conventional calculus perspective, but from a programming language perspective, an automatic differentiation is a program transformation. That is, it takes your program, the program that you want to differentiate, and it turns that into a new program, which gives you a derivative or a gradient. And your ability to do that transformation relies on having access to the model. So it's not just a black box model. I can go in and I can inspect the source code of the model and be able to compute these derivatives, which I couldn't if it was just a black box model. And so one of the things I work on is not automatic differentiation, but a different kind of program transformation for a different need, but all in service of the same goal of inference. And so what is inference in a nutshell? I think of inference as generally an inverse problem. I've got some model, it gives me some output, and I want to know what the input is, or I want to know what a distribution of inputs are. But if that model is a program, a simulation program, then finding the output that would give some, finding the input that would give some desired output is really an inversion program. I have to run the program backwards. Now you can do that in indirect ways, but one of my ideas was maybe we can tackle this idea directly. Can we actually just take a program and try to invert it? Okay, so what do I mean by program inversion? I mean, take some program f, and its output is y, and I want to find x such that y is equal to f of x. And so why do we want to do this? For the reason that I just described, but in particular, we can think of these two examples. So one is inverse graphics. So I have, let's say, some three-dimensional scene on the left, and I have some rendering function which takes that scene and outputs a two-dimensional image. And I want to go backwards to find what is the three-dimensional scene that created my observed image. On the other hand, I might have a control problem, right? So I have a robot arm. I know where I want the hand to be. What are the joint angles which are going to allow me to get my hand to that particular point? So as a software tool, parametric inversion takes some program. So this is Julia code. You don't need to know the details, but the program is some function on the left. And we say, well, give me the inverse of that program with respect to some output, right? So I know what the output of f is, now give me some input. And so the goal is to build a system which is pretty much as straightforward and simple as this, and it just outputs some number 42. Now, how do we do this? So what are the main issues? So one issue is that most things are not invertible. So how can we have some notion of an inverse, which when our forward model is not invertible? And so a simple example is just addition. If I know that f is equal to a plus b, and I know the output is z, how do I get the values of a and b, which would output to z equal to 5? There's many combinations. It could be 3 and 2, 4 and 1, and so on. And so one of the approaches that I've developed is called a parametric inverse. And so the basic idea is I'm going to take my non-invertible function, and there's no inverse to that function because it's non-invertible, and construct this thing which we call a parametric inverse. And the basic idea behind that is, of all the different combinations of x and y, which sum to z, I want to parameterize that space of solutions. So I want to have a parametric representation of all the different combinations. And so let me just show you what that means in the context of addition. If f takes as input x and y, then its inverse would take as input the value, that should be z, sorry, and some parameter, and it returns two values, one for x and one for y, such that if I add them together, I get back the output of the function. So this is a parametric representation of the inverse of this simple function addition. Okay, so most of the time we don't really care about just addition. We've got these really complicated models that we want to invert. And just to kind of skip to the point, the idea is that this composes. So if I've got some complicated program or some complicated procedure, for example, I've got something which takes in two numbers, adds them together, and then squares them, I can take every element in that program, replace it with this parametric inverse. So replace addition with the inverse of addition, or the parametric inverse of addition, replace the square function with the parametric inverse of the square function, and reverse the direction of the order of the computation. And so the big kind of point and the theorem is that this bottom program is an inverse of the top program. And so what this means is that there's a mechanical transformation that I can take to some model, some simulation model, and literally transform the source code into an inverse of that model. Now, you should be skeptical, because if that were true, then many things would be, which we know to be hard would be automatic, right? But the basic premise holds, and we can get into some of the details of why that's difficult in practice. I'll just skip over that. Okay, so the last area I'm going to talk about is knowledge representations. And so one of the key areas in which I work is using programs to represent knowledge. Like how do we, how do we represent knowledge about the world? I think programs are a really good representation because programs, they have this compositional structure. You can include continuous parts, discrete parts, and simulation models of programs, neural networks of programs, but more generally, the space of programs is a very rich language. And in particular, going back to my Galileo example, if I think about different conceptions of the universe, how can we build a system that could learn like or reason like Galileo or Newton and so on, right? What is the space that represents all the different kinds of theories that scientists have developed over the world? For example, Newton's theory, F equals ma, or Copernicus had a model. Going back further in time, there's even older models. The structure which is able to represent this this very rich notion of universe models doesn't seem like it's a continuous vector space. It seems like it has a lot more structure. And so we haven't got quite there yet, but one of the problems that we're working on is this notion of program synthesis. How do we learn a program from data? And so let me just show you a quick example of that. Okay, so here is a kind of an ongoing project, and this is done with sorry if there's background noise. This is done with Josh Tannenbaum, and most of the work is done by an undergraduate called Ria Das. And the basic idea is that we have this game-like environment on the right-hand side, and this is a program on the left-hand side. And I can interact with this, hopefully. Let me just try to. Okay, so it's a little bit laggy, but you can see when I click, these purple things come down. But even that is an inference, right? It could just be a coincidence. Somehow it seems to be the case that when I click, that causes this purple thing to come down. And if I press this blue thing and I click, you can see that something's somewhat changed, hopefully. Maybe there's some bugs going on. Okay, there's a slight lag, but you can see this kind of water going down. Okay, so the main point here is that this little world is not particularly interesting. It actually just models a water plug, but it's a very hard thing for all of modern machine learning to learn, because you've got these things, when I press this yellow thing, nothing changes. It's only when I make this further action in the world do I see the change, do I see a change in state. So when I click now, I see these yellow pieces. When I click this black thing, things should disappear, right? And so what we're trying to do is to build a kind of a system and a paradigm of learning where an agent will interact with this kind of domain and produce the entire source code on the left-hand side, right? In other words, to learn the model of the dynamics just from observing and interacting in the world. And this is a very hard problem because it's not continuous. It's a very large, relatively speaking, program. It has a discrete structure. And if you've thought about this a little bit, you can think the space of programs of this length is enormous, right? And so how can we figure out how to synthesize this program from data? And so in this example, we can actually do it, and all of these examples we can do it. But this is part of the discussion. So I will end there, but those are the main kind of points that I want to focus on, like knowledge representations, algorithms for reasoning, and different modes of reasoning.
Thank you so much, Zena, for sort of charting out this landscape. Before asking Kyle to react a little bit to the work that you presented, I'm just burning with curiosity, given your background in cognitive science, right, as well. So in terms of reasoning, are there sort of limits and capacities that are actually hardwired? Or is this not even a useful question? I mean, I'd be happy to be told, disabused that this is not a good question.
Yeah. So limits that are hardwired. I think the answer is I don't know. I don't think anybody knows. It seems like we've been able to figure out a lot about the universe. People like Carl have helped us do that from really sparse observations. And so I would hazard a guess that there is a universality to our ability to reason, which is bounded only by kind of the physical constraints of the world and our ability to compute. Right, there's computational
and not
constraints.
So much by neurons and neural structure and connections between neurons. Okay.
Right.
Great. So anyway, Kyle, I turn it over to you to begin your sort of engagement with what Zeno presented.
Sure. Yeah. Well, I mean, it's always, I think well, not that we should look for something to disagree on, but we should also not be boring and just, be like, because I think we were both excited about a lot of the same things. And I'm thinking back to my talk, I didn't really get to say too much about some of this buzzword of probabilistic programming, which is very related to what's, but I do think that, this idea that when you have some story for how the data came to be, which is, as a physicist, if you're talking to another physicist, it's a causal story. It's very natural. You can take that story and you can code it up into a computer program. So if you don't feel comfortable thinking about computer programs, I think you're not going to really miss anything if you just think of it as the story about how the data came to be. And what's nice is that, maybe you could come up with a computer program that has a very unnatural story, but still produces the same kinds of outputs. But I think that's not the spirit of the conversation. The spirit is much more that the computer program is really just, capturing what you think the actual underlying, story is. And there are so many different ways that things could play out. And I think it's really interesting when you think about statistical inference, and statistical models. I introduced these terms of latent variables, which are, random things that happen in the process of generating the data that you don't get to see. And examples that I give sometimes, if you think about like the creation of the solar system, how did the moon happen? Well, maybe some big thing came and smashed into the proto-Earth and, knocked off a big piece. And there are all these little, early on it was a disk and things started to form. I mean, there's some story that's going on and you could simulate that and it would have all sorts of details about individual rocks running into each other and things like that. We don't get to see any of that. And if you actually wanted to simulate it, it's just enormously complicated, like what would be going on. And especially when you introduce, in the story of like rocks coming, you could imagine like, did this thing split into 2 pieces or 3 pieces, or did it just stay together as 1 piece? If you wanted to follow that through the simulation, you get this just incredibly highly structured space of possibilities that doesn't look like it doesn't look like some vector and, like a 1,000-dimensional vector. It's this very rich in, like graph structured thing or something like that. And, so much of statistics has not really dealt with, a lot of classical statistics didn't deal with such structured objects. And I think one of the things that's really interesting right now is we're seeing this kind of, it's partially computing, it's partially, it's hard to tell exactly what's going on. I think, to some extent, I think what's significant about machine learning is that the ambition level has just jumped so much. Like things that you could have said, but that everyone would have laughed at you if you thought you were going to actually go after it. Like in some sense, what you were just describing, your program inversion, sure, yeah, you can do that. You could have said that like 10 years ago, but everyone would be like, but that's never going to work. Like, why would you try to do that? But now, all of those things are on the table, and there are all so many things that are working at a scale where, you wouldn't expect them to, that it's just kind of it's really refreshing because you're going back kind of to really the first principles. It's like, instead of being restricted by all sorts of, constraints that make people kind of have all these ad hoc workarounds, people are like kind of emboldened to go back to like really first principle approaches and revisit them. And it's just surprising that a lot of that stuff is happening. So to me, I think, the idea that you're going back really to like core Bayesian inference kinds of ideas, but the types of models that you're working with are just so elaborately complicated and they map so much more onto the way that we talk about the world. It's really exciting. I don't know, that's my first reaction, I guess.
Yeah, no, so lots of things to think about and talk about. So one of the phrases that you had in your talk last week was the idea that simulation models are causal models, right? And this is an intuitive thing to me and to many people. Part of actually my PhD work, which I didn't really focus on here, is that taking this idea literally and saying a lot of the kind of the theory which has been developed in the context of kind of causal graphical models can be extended to a richer class of models, in particular programs. So you don't, the particular formalism isn't that important. Actually, you can have a much richer formalism. But I think there's this underlying question, and maybe to some degree it's philosophical, which is like, what is it that makes simulation models causal? Are they necessarily causal? Or can we think of simulation models which aren't causal per se? Like, what is the?
I mean, Zena, aren't they? I mean, just a quick question to both of you: aren't simulation models by construction causal, right?
Yeah.
Can you make a causal?
That's my question. I mean, I think it is, but I'm kind of curious to.
I feel like you start really getting into lots of interesting subtleties where you start to dissect different notions of causality. And I kind of pointed at two of them in my talk at the beginning. One is if you have a simulation that's like a totally deterministic evolution of, you have some initial state and you just let it go, okay, it's causal in one sense, but it's also not causal in the other, especially if it's time reversal, symmetric, like the arrow of time is confusing and it's all one object, it's all one thing, and so, when you think about like, I don't know, space-time unfolding, is it evolving through time, or is it just one object of space-time that the whole future and past are all there, so you get, but then there's another sense, if your operational definition of causality is that there's some effective time ordering, and you have states, and initial, one state goes to another state, simulations are almost by definition causal in that way, because they unfold as the computation plays out, right? But then you can have stochastic components and all sorts of things. The other thing I think that's interesting about having this grounding a lot of the discussion about causality in this language is that some of the things that seem can be confusing, they just they're revealed in a very precise way. So for instance, I could take, if I wanted to, in the language of like unipearl causality, if I want to intervene and go set some value to something, like imagine I have a particle and it has some energy and some momentum and some mass. Like, what if I just want to move its energy? Well, like that breaks some condition that, that there's some relationship that would normally be there. And that's like not an admissible kind of intervention, right? And, if you actually try to do this in code, like it's kind of weird, depending on how you wrote your code, maybe it will continue to proceed, but you'll just get nonsense out. Or maybe it will have a, segmentation fault, because like at some point it assumes that this condition is satisfied, so you get, it's just kind of, it lays bare a few of the subtleties around causality, which I think often are discussed in very like, not that there's anything wrong with philosophy, but in a philosophical language where I think it can be hard to latch onto, but it can be kind of grounded in a very concrete term where you can separate out, slightly different notions in a clear way.
So 100%. So we have this paper, and it's called Omega, a language for counterfactual reasoning. And the point of this paper is to define what it means to perform an intervention on a general program. And one of the questions that arises is exactly what you just said. Like, what if you do some intervention which breaks the semantics of your program? Like, it makes it invalid. Like, is there some scope in which you just say, well, that's not allowed, or do you just allow it and see what happens? And then the more you think about it, the more you get into this question of like, what is an intervention in the first place? Is it just some arbitrary, so in the common literature, an intervention is, the reassignment of some node to some new value, right? But when you go to more expressive models, that doesn't seem sufficient. And so is there some like underlying more fundamental logic, which is less tied to one particular representation of a causal model, which would say this is a valid intervention or not?
Right.
And then going to your a point you made earlier, if you think about kind of these more abstract models, so like, let's say I've got some low-level complex simulation model, like let's say a physics simulation, but I want to be able to say like some high-level intervention, like, what if, I don't know, like what if I threw the ball or something? Right? Like, how do those high-level interventions interact with kind of the low-level microscopic model? I think is another related question.
Yeah. I'll pick up on a comment that I see in the chat. So Jeremy Zucker said simulations don't need to unfold in time. One could specify constraints among all the variables, add an objective, and treat the entire simulation as an optimization problem. I mean, I don't want to get into the weeds too much. I think that, I think the language that I had used was that, that there's some effective notion of time, meaning that like literally as the computation evolves. So like when you compile the program and you run it, like there is a serial operation that's happening. So there's some effective notion of time there that might not have anything to do with like time, like as we think of it and, like on our watch or something. And that's kind of, that example is kind of interesting because I think, and I tried to sort of, couch my statement earlier that you can have a simulation that produces kind of the right output, but the way that it unfolds, the story that it tells might have nothing to do with how anyone thinks the world works, right? So in that sense, it's totally anti-causal from like a physical point of view. It's not like a plausible scenario for how it actually came to be, but as an operational definition of what do I mean by causal, like you could use that like, define it and like, give it a new name if you want, computational causality or something like that. It's some very well-defined notion of causality so even in that situation, that example, if it's an optimization problem, like solving the optimization problem would be like the causal model for the data, which is very unsatisfying from the point of view of a physical, a story, but totally operationally well-defined. But it also makes you think, well, maybe not, maybe, like classical mechanics is expressed as can be expressed as Euler-Lagrange optimization problems, maybe somehow that's actually how the universe is implementing things, who knows, right? But I think that's part of what's interesting about describing it that way is that, I don't know, it allows you to ask some pretty weird philosophical questions while still grounding it in a very concrete, actionable set of definitions.
Right. And it seems like it places the burden on the modeler to ensure that the causality in the world that they care about is mirrored in this notion of computational causality, which you use to construct your model, which is kind of a weird but maybe necessary thing. Right.
Yeah, or at least it's a route. I don't know if necessary, who knows, but like it's a it's a way to frame the discussion that also I think and
that's what I meant when I say you have to put it in by hand, right? That there's a mapping that you do when you
yeah. And I made some references to this kind of normative discussion and things like that. I think that's what's a little bit interesting is if you want to then talk about causal inference from the point of view of reasoning and there's a part which is about it being a useful thing to do that allows us to learn efficiently from limited amounts of data, right? And so when you start to frame it that way, you can also, it makes it a little bit easier to talk about sample complexity of learning algorithms and these kinds of things, and sometimes you can make some pretty strong statements, like they're not just like the best algorithm that I've thought of today. I mean, you can kind of like show like there's no way you're going to learn this without like exponentially more data than if you thought about it in a different way, right? So and I think those are relevant. I think those complexity issues I don't think are just like a matter of computation. They're not like fundamental. I think those things usually are probably something strong signs of something that's actually much more fundamental. So I do have a question for Zina, I guess, is like so you talked about kind of this inverting the programs and things like, and I think that's super cool. And I think, this whole, what that example, probabilistic programming, automatic differentiation, many other that are things that are this kind of high level program transformation are really interesting set of ideas to think about. But you also gave this example about, the argument that the moon is not perfectly smooth, where it's very fast and loose type of argument. And when I think about, I don't know, like, how I think about like what's going on, say at the LHC when something strange is happening in the data and I want to try to figure it out. it's definitely in the fast and loose category. I'm not like iteratively inverting my mental model for like how the low level, particle interactions happened or something. So I'm curious, since this is squarely.
Kyle, I just want a little bit of a clarification. So what do you mean by fast and loose? Are you talking about eliminative reasoning or?
Oh, well, this example about arguing that the terminator of the moon is wiggly, it had a logical element, but at the same time, it's sort of based on, there's an observational component, and it's not really, I don't know. I mean, I guess a lot of other examples of human reasoning like that were given at the beginning, like the car accident and the the weather and stuff like that. It's not, I don't think, I don't know. I don't feel like humans are doing some kind of logical reasoning at that level. It's kind of some approximate. I mean, they're manipulating high level sense of reasoning in that way, but it's not so formal. And once you get into something that's more complicated, where that you get this explosion of possible paths, the inverse of that problem is, has an explosion of possibilities. I don't feel like we're like keeping track of all the possibilities. That somehow we have some effective way of
filtering.
Of kind of playing out entire, like not individual scenarios, but like whole classes of scenarios that kind of are placeholders for distributions of possibilities. And we manipulate them just very efficiently, and we were able to like pick the right abstraction to do that. And to me, that's it's magic. I don't know, like I don't know how we did.
I mean, I wonder if that's because we have some kind of mechanism to eliminate possibilities, right? So that we reduce the complexity, basically, as you're saying, right? Somehow we are able to reduce the complexity of possibilities in human reasoning.
Yeah.
So, wait, did you have a specific question or just like?
I'm just curious. Thoughts? I mean, I just felt like the two different things were, and the two things you showed were, in some sense, they have the same underlying drive to them, but they're kind of opposite extremes. Like one is a very, you're making this reasoning. I don't think people are going through all these possibilities. And then the other example was this kind of a program, a transformation, which is going to have this explosion of possibilities, right? And so.
Right. Yeah. So I think, thinking about what I call this kind of, approximate logical reasoning, or it's not quite formalized yet. I think that the goal there is to characterize what I think we do all the time, right? So maybe if you went home and the window was open, you might be like, well, my partner must be here, otherwise it wouldn't be open, right? And so we do this kind of thing all the time. So when you come to that conclusion, are you doing like a massive simulation of all the possible worlds, right? But it's not. I don't think it's just about efficiency. It's a different form of reasoning, in the same way that producing a mathematical proof is different from sampling, right? It's not just like a different kind of algorithm. It's a different nature, right? A mathematical proof has this kind of logical deductive structure, right? This tree structure, which can be formalized in many different ways. But I don't think that has been kind of adapted to common sense scenarios. And so part of what I want to do to try to do is to think about like, what is that? Because it seems like pretty fundamental. Like way prior to Galileo, there were many people who came to the conclusion that the moon was mountainous, through this kind of logical, informal, deductive reasoning, back to Aristotle's days. And so it seems to allow us to come to insights way beyond our observational kind of capacity. But it's, what it is, I don't know, but I just feel like there's a whole. And part of what I'm trying to convey here is that aside from the current paradigms of reasoning and inference, which parametric inversion is part of, this kind of the second thing, I think there's just many more interesting modes of reasoning. So to give you another example, one thing I think about a lot is this notion of actual causality. So going back a little bit to this notion of causality, simple question, right? Did A cause B? For example, like did I threw a rock, it hit a window and it smashed. Did my throwing of the rock cause the window to smash? Right? It sounds quite simple. And how can you make a machine do that kind of reasoning? And it turns out that it's incredibly hard, right? It seems simple. Like you might say, well, like had I not thrown, then the window wouldn't have smashed. That sounds like a reasonable thing, but it turns out that breaks down in many different ways, because like, what if something else would have caused it to crash anyway? And so this is a basic question, which we don't have the definitions right about, let alone the algorithm, don't have the right definitions. And what it points to, the more I think about this, is like this notion of causality as almost like a epistemic question. Like when I think about causality, is it really about, the underlying world, or is it more just about human minds, right? Like, is causality part of the world, or is it part of our mind? And so is our hope to get these kind of pristine notions of causality a fool's errand, because fundamentally they're kind of messy concepts, or is it more this kind of metaphysical thing, which, a little bit like probability, where there is this underlying pristine theory, we just have to discover it, but we haven't got there yet. So maybe that's a little bit abstract, but that's kind of how I've been thinking about it recently.
Yeah, and I think it's interesting. I mean, definitely this. What to say? I mean, it goes back a little bit to, this idea that you're trying to come up with like plausible explanations for something.
Right.
I think points a lot to this idea that you have, you don't, it's not that you're just running some program that was already written for you. You're kind of constructing the program as you go. Like, could this have been the explanation? And if so, then you can kind of mentally simulate what would happen and the consequences of that thing. But to do so, you kind of have a vocabulary of different, or an ontology of different kinds of things, and how you can compose them. And a lot of programs, they're just more rigid versions of the same thing, where the types of stories, it's sort of a choose your own adventure, but it's very, very structured. Here, you kind of like on the fly get to add things. And I think, that in my talk, I mentioned a little bit about hypothesis generation and stuff. And I was trying to, contrast against, if you just think about like a lot of kind of black box machine learning algorithms that maybe can solve like the particular scientific task that you're on right now better than anything else on the market, that's true. But like, what do you do next, right? Like if you, you test that particular theory at high accuracy and you get the most out of your data, and that's great. But like now what experiments should you do, right? Like if you somehow can't introspect, like or something goes wrong, like the data does not look like you expected from your theory, like what do you do? And the human way of doing it, even though maybe it's not squeezing everything out of the data, like it has this explainability component to it, because the way the data is being analyzed is composed of a bunch of things that you understand, and then you can go inspect it every little step of the way. And if anywhere in there you can isolate where things went wrong or were unexpected, and then that motivates generating new hypotheses, which are new stories that might explain why it went differently. And I think that's absolutely key to how science as I know it, and people that I know that do it, how they would approach such a problem, and what's good is that, sure, it looks different than kind of the current AI, but it's adjacent to stuff that's happening. I mean, you're doing it, I'm doing some stuff. So it's not like some radical, like, oh, we're on the wrong path. It's like right now we're figuring out how to do these hybrids between, probabilistic programming that have, take advantages of the powerful parts of current deep learning things, and, mix all this stuff together. So there are a lot of people that say, oh, we're on the wrong path or whatever, but I feel like actually these are starting to come together in a way that looks very exciting. And I think, I don't know. Yeah.
And one of the things that I think is interesting, and I think it was in one of your charts to some degree, right, is this notion that the scientific process is a lot more expansive than, often the kind of the more narrow view that we give it. In other words, like, if your experiment didn't work, or you got some strange observations, you might invent an entirely new theory. You might invent a new form of mathematics, right? It's not just like a constrained action space. You can really change the fundamentals, at least like historically humans have. Like, you're building upon this like massive foundation. And so I'm really interested in like, how do we, like, all of these things that we take for granted, when, by the time we build a modern machine learning tool, we've already taken for granted calculus and, what are the objects that we care about. All of that is kind of given by the humans. But if we want to build machines that can do that part of the process too, what do we have to give them? One question I wanted to ask was around this, this notion of like modeling and representations of knowledge. You have this term collaborative modeling, which I think is great. I wish I invented it, but I'll certainly steal it. What do you think are the kind of the key components of building a collaborative model at scale? Like how I'm very curious, like your interpretation of this phrase, but I'm particularly curious, like what are the kind of the barriers which prevent like me as, let's say, an epidemiologist and somebody else as, I don't know, like a climate scientist from kind of getting together and building some model which takes into account all of these different components in some coherent and cohesive way?
Yeah, wow, that's a great. I like how you threw it back at me. Yeah, well, I think there's a part which, when I first coined that term, it was applied to a pretty narrow set of problems, which was really kind of how do you do statistical modeling, kind of really in the context of sort of like LHC, where there's lots of different data sources or views of a larger data set. That things are related in various ways. You want to. Previously, it was very top-down and rigid sort of structure to be able to bring those things together, and it didn't scale well. And then at some point, we've figured out a way to be able to let people kind of work in a more decoupled way, understand their part of the problem, let their be the experts in their problem, figure out how they want to think about it and parameterize it, but still maintain the ability to bring them all together in a kind of and do some coherent inference in the end. And that was and once we introduced, there's just some underlying technology really that kind of in terms of model sharing and interfaces and things like that. And once we got that part right, there was this like literally exponential explosion of complexity, which was amazing to watch, and it was kind of scary also because computationally everything became very hard very quickly, and so we had to figure out how to keep up. But what I do think is kind of interesting, and it's a little bit more on the meta side, is that in this, when we went to started working on these like simulation-based inference problems, what I love about that is that it's really like a lingua franca for methodological experts and domain experts to be able to really effectively collaborate, because there's somehow you encapsulate a lot of details about your problem and you expose some way of talking about it, but literally through interfaces that methodological people can work with, where if they don't need to know the details, they can kind of be shielded from it, but you're not losing a lot of the real complexity that's going on inside there. And I think that that it's just true that I'm now able to have conversations with neuroscientists and cosmologists and epidemiologists and phylogeneticists and stuff at a level that I've never been able to have before. And actually it's also been a way for me to understand their problem much more efficiently, like even the details of their problem, because like the onboarding of that is really useful. But there's a part which is it's really, actually much more on the like software engineering interface level, which allows you to actually build models and do compositionality like you would want. But it's very actionable in that sense, but it also kind of pays off in a way that you would hope, a bigger kind of, more ambitious answer to your question, that this is something that sounds like as lowly as like, good interfaces or something, but it actually, I think, sort of starts to realize that. And it's really compelling idea because, if you think about COVID simulations, like, or epidemiology, the simplest ones are you just have some uniform population that doesn't even necessarily exist spatially. It's just like there's some number of people have it. There's some chance that, they're going to give them, and then you get these like differential equations, but those differential equations are really like all averages of something. They don't look like have some underlying stochasticity, and they don't like, now let's say I want to actually think of it as actual people, and they're actually live in actual cities, and I know where they are. Like, it can be scary sounding, but I mean, if you just, in terms of the richness of the model, like, this group of people in this neighborhood behave a little bit differently. You got like the 20 somethings over here, and you've got the, other people over here. They have different patterns. They interact differently with each other, and you can definitely see the story about how you would actually build up such a model where people that know about the different pieces contribute in some much more collaborative way. And that's like that's exciting. I mean, you have to be careful, but
I mean, yeah, I think like, as I've thought about this more, like, it seems like one key thing is, as you just said, like, how do you have these entities which are shared between different groups? So one model is talking about people or populations of people. The other model is talking about people at a more fine-grained level. But as humans, we just got to communicate and say, hey, both, that's about people, or maybe we use a variable name to indicate that that's a person, right? But it seems like a lot of the knowledge that we have about the world is not actually in the model representation. It remains in our heads, and then we communicate with each other to tell us, what that means, right? But it seems like if we want to be able to build, systems that can really reason, they're going to have to, in some sense, represent the entire stack. So all the way down, it's not just like an abstract variable, but this really represents a human in some sense.
Right. I mean, it's a lot of implicit knowledge, right, that is brought to bear.
Right. And then the second thing is, like, if you have different people contributing different models, which may be inconsistent, right? You need some way to integrate that, that knowledge together, right? And is there a kind of a sound way to do that, or is it more like a heuristic approach that we have?
But I mean, there may be instances where you not only need to integrate, but you may need to arbitrate, right, between the two.
Yeah.
I was just looking at the questions, but I think it's well. The last thing, I mean, I just tag on that. This whole story also is a natural path to being able to try to do the thing where you have the different hierarchies of representations. If you can figure out some way of having this kind of ontology and almost like a type system over the different kinds of entities, you can certainly start to make things that are hierarchical, or some many to many, or like, here's an alternate way of thinking about the problem with a totally different set of things, and you may just switch from one modeling paradigm to another modeling paradigm. You might not be able to mix them, but for one task, one is appropriate and the other one's appropriate, or, who knows, or be able to telescope in and out and refine the detail if you need it. And if not, enjoy the benefits of working at a high level. But if you have inconsistencies and stuff, I think that's I think that's which is certainly real. I'm guessing things get a little bit messy at that point.
It goes to somewhat deeper points. So going to the example you had in your talk with the machine, the kind of the bean machine, where you had it produced this like non-conventional distribution, and as you said, like, it's a deterministic process, but you can think of it stochastically, and so I guess the question is, like, I'm kind of coming from the more subjective Bayesian perspective, which is that when I think of that as a distribution, that's more like my kind of belief, right, about its outcome. And so when we go to languages or representations for probabilistic knowledge, there's a kind of a subject. There's like a hidden subject, right? If I say X is some normal distribution, maybe there's like a hidden extension to that phrase, which is like X is a normal distribution believed by me. And so if we want to integrate lots of different knowledge from lots of different sources, maybe we need an explicit representation of where the provenance or the sources of these beliefs, so that if X is a normal believed by person X, and Y is X is a a beta distribution believed by person Y, there's some way which we can take kind of the relative like credences of these two individuals to say, well, okay, I'm gonna integrate that in some consistent way. So maybe that's a long way of saying that maybe an integral part of kind of a sound way to integrate knowledge is to make explicit the notion of subjectivity in our probabilistic models. I think that's a kind of
I think I alluded briefly to that in particle physics, it's one of the kind of last holdouts where Bayesian inference is not fully embraced, but it's partially because when you start talking about things like the prior distribution on some fundamental constant of nature, or like, does this fundamental particle exist or not, or does this symmetry of nature exist? Does nature have that symmetry or not? Like, you can't base it on data. So you really have to embrace the subjective version of that. But there is not an agreement among physicists, right? If there was like some, wide agreement, then maybe no one would care. But when you have wildly different subjective priors associated to different scenarios, like what do you do operationally, right? It's tricky. I think that this would be an entire other hour discussion, but I think there's a part which is maybe worth saying is that oftentimes we couch a lot of this in like Bayesian inference and a lot of these things as somehow like there's like a rational or optimal way of doing it, and that's like the sound way kind of presumes that like we should be trying to do something that's like consistent or whatever. There's another view which is that we're not really optimizing anything. We're not like we're just doing, and there's kind of dynamics, and especially when you think about like a very heterogeneous group of people that have heterogeneous access to different pieces of information. And then you just think about behavior, it's not necessarily, maybe in some cases it's well modeled by something that looks like some Bayes optimal something, but in many other cases, maybe it's just like I was hungry and that's why I did that, and so then you get into a question of what exactly are you trying to describe? Are you trying to be descriptive or prescriptive in the whole story,
So, Zena, there's a question for you in the chat. If everything in the ontology stack should be up for evolution, can anything pristine at all, as in your characterization of probability theory, remain? And to Kyle, can your statement that the particle physics simulators already express a wide variety of alternative theories be taken literally enough to mine it for grammars of nearby theory space? I guess the expansion of permitted theories. Interesting question. Zena,
Yes,
do you want to have a go first? Yeah.
I'm trying to interpret it. So I think I would like some clarification, but maybe I'll make a guess exactly what you mean, Boyan.
I'm not sure how the word evolution is being used there.
Yeah, I was going to say, Boyan, could you clarify and type in the Q&A? I guess really, what do you mean by evolution there?
I can respond to the other part if you want to not have good time. Or maybe he wants to hear the answer and that's not fair.
Go ahead.
Yeah, I guess I'd say that, I had made the comment, last week that, there's a part where when you're doing simulation-based inference, it seems like, well, how do you learn anything new? Because you already have it in your simulator. That seems reasonable. And I tried to reframe that as that, like, whenever you're doing inference, it's kind of in the context of some model, right? So like to the extent that inference looks like this inverse problem, it's an inverse of something. And so like that there's a model there kind of, to start the discussion. So so in the case of particle physics, the model is not like the standard model of particle physics, which is a specific theory, is like one point in the space of possible theories that can all be expressed in the language of whatever quantum field theory. And so that language of quantum field theory allows you to express all sorts of other possible scenarios and universes that can be described. For the most part, I think most professional physicists feel like essentially anything that looks remotely like is anything like our universe is going to be expressed in that language. So in that sense, it's a very expressive one. And if you wanted to work outside of that language, you really, everything starts to kind of like you really have to revisit everything, and so in terms of mining it for the grammar of nearby theory space, I mean, in some sense, it depends a little bit on how you mean it, but I think in many senses, absolutely yes. And there's a very systematic approach for kind of how to, like if you go to some theory, how to expand around it in a nice way, and to the grammar is like really very explicit. And it's one of the things, actually, another one of Josh Tenenbaum's former students, Brendan Lake, who's here at NYU, he and I have had various discussions about, this kind of, can we operationalize like rediscovering the standard model, where you operate in this kind of grammar of theories that's restricted and quantum field theory, and it would be computationally expensive, but I think you absolutely could. And the part that's a little, on one side, it sounds super ambitious. On another side, it's kind of so clear how you would go about doing it that it almost is like, is it worth the effort? You know, like it would. So it would be great to do it and to say, like, here's an automated algorithm that like basically went through the space of theories in some, you know, structured way, and basically came upon the standard model and said, this is it, and I don't have any evidence for anything beyond it. And it would be fun to do. I think it's kind of, in another sense, it's kind of clear how you would proceed.
Right. So Zena, there's a bit of a clarification from Boyan.
Yeah.
Yeah, did you see that? Yeah.
Yeah. So yeah, I think I have a better sense of this question. So going back to what you were talking about earlier, which is that scientists change the foundations, both the mathematical foundations and the ontologies which we use in various different ways. And so I think Boyan's question is, if you permit that, then how do you prevent your house from just like crumbling? And how do you, it seems like if there's no kind of stable foundation, then anything goes. Maybe that's my interpretation of this question. And the answer, yeah, I don't know. I think maybe when we think about a theoretical framework, maybe thinking about it less as being like true or not true, it's more like useful or not useful. And I think if we maybe go a little bit to what you were saying earlier, Kyle, what is if we have some kind of goal, which may be to predict the future, which may be to, make valid inferences, we can think about all the layers below as like, either in service of that or not. And so I think provided that there is some kind of foundational, there is some kind of external objective, I think we can be flexible with these foundations as long as they're in service. And to your kind of example, like probability theory as pristine, I think it's a pristine model of like rational thought, which is really dependent on, agents. Like I think it would be hard, maybe this is where Carl might disagree, but I think it might be hard to kind of justify probability theory as being like uniquely good in the absence of rational agents. But that is kind of maybe a controversial claim, but yeah, I'll leave it there.
And I guess there's another question about counterfactuals. I guess the reference is to, there was this book by, and this work by David Deutsch and Chiara Marletto, The Science of Can and Can't. I remember reading that, A Physicist's Journey Through the Land of Counterfactuals. I think the question here is, counterfactuals can serve as an important thinking tool, right, in the deeper exploration of causal connections and alternate scenarios. And so the question is that, they argue that describing physical laws in terms of counterfactual tasks they generate, and they counter possible tasks that cannot be generated. And the question is this kind of reasoning seems very similar to the way that Galileo was able to infer the non-smoothness of the lunar surface, right?
Yeah, there is something very counterfactual about it, right? It's this kind of, if this were true, right? The moment you have a would in your sentence, you're kind of in this counterfactual regime. And so it does seem that this kind of reasoning both touches on counterfactual reasoning and also this kind of proof by contradiction style reasoning. Maybe those two things are equivalent in some fundamental way. I'm not certain yet. But I think it's interesting, again, going back to this earlier question of what is the status of these kinds of statements, right? If I make a counterfactual statement, is that something that's true or false, or is it just?
Yeah, I was just going to say it's not testable, right? I mean, I'm kind of uncomfortable in a way. I mean, they're tricky. Counterfactuals are quite tricky, right? Because they're not testable. And so what is that? For example, in science, I've never quite understood what sort of their utility is. Because it's not testable, right?
But even I guess what what lies at the foundation of a valid counterfactual, I think, is the validity of your model in the world, right? If you have a correct model, then in some sense your counterfactuals are correct by construction. And so even though they're not testable, there might be a sense in which they can be correct or not correct which gets pushed down to the question of, is your model correct or not correct? But that becomes complicated because,
right. Yeah. So, I mean, I was thinking of, the kinds of examples they use, right? I mean, I remember one, I think, there's something like, the possibility of building a steam engine, which existed long before the first one was actually built, is something they give as an example of a counterfactual, right? And I mean, and this is so as it exists in the domain of the possible, and its functioning does not violate the principle of conservation of energy. And whereas the sort of counterfactual property imposed by the laws of physics that, is that you cannot, for example, build a perpetual motion machine, right? I mean, so these are the sort of ways in which they use it. So, I mean, it's a way to permit ourselves to sort of entertain the idea of possible worlds, right?
Right.
Or alternate universes that are like variants of our current realities. I mean, that's where I get stuck and say, well, it's not testable. So,
right. I saw an article recently which was it's like a logical philosophical article trying to give a formal definition of what a law is. And the way they're trying to do it is say, well, it kind of must remain true under any counterfactual scenario, right? So there's a difference between saying, I haven't done this yet versus this is impossible, which is quite a hard distinction to actually make. Anyway, I don't know, Carl, do you have thoughts on these things?
Yeah, well, one of them is that, I think that on the counterfactual, it makes sense, when coupled with a model, because like then you can basically, with that model, you can sort of simulate, other scenarios, right? And so it's not testable in the sense that you can't like literally with that, go back and change the thing that happened a different way. So for that particular instance, yes, it's not testable, but it's testable within the model, and it has consequences, and so like, so then you, if you think of it in more of a decision theory way, like you're going to use your model, answer, ask the question, what if I had done blah, 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 simulate or something, reach some conclusion. And based on that, you're now going to take some informed action in the future. If your model is bad, then you may end up, walking off your cliff or doing something bad. If your model is good, then it may help guide you to, so in that sense, it has consequences, but it's maybe not testable in a very, strict way. Also, if you think you can somehow like re-prepare an equivalent state or something like that, and then sort of do it again, and you have some notion of exchangeability, then
it sounds like if you are able to simulate it, then it's testable in that way, right? In the way that simulations allow you to test.
And then but the other example where if you can somehow re-prepare a similar initial state and do it again with the with the opposite, with a different the counterfactual scenario, then it that's effectively simulating. You're just using the actual world to do the simulation. So, but it still involves a model in the sense that you're saying a lot when you say that I think this initial state is the same as the previous initial state, right? Like, how do you know that that's true, right? That's effectively a model in the sense that you think that whatever you did to prepare this initial state is like equivalent. And then, but in both cases, whether it's simulated or it's like actually like in a lab and doing something, you're still bringing some assumptions to the table, and you look to see what happened. You reach some conclusion, and then you act accordingly. And if you're wrong, if your process of preparing the same initial state actually didn't take into account like the temperature in the room, and that's important, then you will reach the wrong conclusion, and your car is not going to work.
I guess a lot of my skepticism of counterfactuals, really, I have to confess, comes out of a bias, is that this relates, this is sort of an offshoot of this idea of multiverses that people are constantly playing with, this idea that the multiverse, there's an infinite number of possible universes, and it has obviously broad explanatory scope, so it's kind of attractive, but nothing about the multiverse is really testable, right? So I think that is where that's where my sort of notion that this is not so testable, right? Is that
definitely have had a multiverse talk in this series, so.
Right? Yeah. So, I mean, and I always get stuck, right? When I try to put the kinds of conceptual things that you both talked about and in sort of the multiverse frame, right? So, if the universe, in principle, you can imagine universes for which, the Newton's law of gravitation takes on a completely different form from ours, right? Or a multiverse in which gravity may not even exist, right? So how would you discriminate between those universes where Newton's law merely takes a different form, but one in which gravity at all doesn't exist, therefore that law doesn't exist? Anyway, so I think it's a different rabbit hole that we don't want to go down. And there's a question that somebody has asked Zena for that. Do you have a reference for the article that you just mentioned about the discussion of laws, like what the relationship between a law and the counterfactual, that law is valid?
If you email me, I can find it somewhere in my internet history. I do have another question if you have time still for
yeah, of course. Yes, yeah, please.
Yeah. So this notion of like abstraction or different models at different levels of fidelity has come up a few different times. And I think, as maybe you indicated, it's also it seems integrated into this other question of like, how do you do this kind of collaborative modeling? So an example that I used to say when Obama was president, I would say, like, suppose somebody asked me, or suppose I asked you, like, how tall is Malia Obama? This is a kind of a very not common question, but a very ordinary question, right? And so most people don't know the answer, but they can make a guess, right? They can say, well, maybe, her father was a president, and presidents are kind of typically tall, so maybe she's this tall, or or I know she's a woman, maybe she's, and so all these different kind of sources of information, maybe her ethnic background, that will come to integrate into your conclusion. And so going to my question, when I think about how do we build kind of very large collaborative models, I can think of almost like a multiverse of different models that are connected together. It seems that one integral part must be the notion of different models being more or less abstract than another. To give another example, when I think about something as simple as a light switch, right? If I understand the light switch as just some binary model, press the light switch, the light comes on. At another level, I studied electronic engineering as an undergraduate. I understand the electric circuitry behind it. At another level, I'm just a human, so I understand the physical actual geometry of a light switch. I have all of these different forms of knowledge, and they all influence how I interact with the light switch. So if it doesn't work, right, my light switch doesn't turn on, it could be because the electronics are broken. It could be because the London power station is down. It could be because the mechanical switch is broken. And I'll choose the right level appropriately, or at least I'll try to. And so going to your simulation-based models and simulation-based inference, do you have an intuition about how we can build representations of models which can capture these different levels of abstraction, or these different perspectives, or these different sources of knowledge in a way, again, which is coherent? And is that a different question to this collaborative question?
Yeah,
sorry, long question, but yeah.
I mean, that's a topic that I'm very interested in and sort of wanting to work, well, I'm working on, but in various levels. So, I mean, part of it is, I think, also just asking some easier questions at first, which with those kinds of questions as a goal. But you even get into the situation of, say that you already are kind of handed the different, models at different abstraction levels. And also you probably want to prepare for the fact that the ones that are at like a higher level of abstraction maybe are not quite as accurate, right? So how do you incorporate the fact that the fidelity of the model in terms of how well it describes the data, and how would you use it, right? Like, say you have those models, how are you going to use it? So I think about things kind of in a sort of reinforcement learning or decision making kind of scenario, which is, if I'm going to use this for planning, like one way of thinking about world models that makes them very concrete is when you think about using them for planning or decision making, right? And so that helps ground the thinking a little bit, which is, how, if you did have them, and that the different levels of accuracy and different trade-offs in terms of how expensive they are to run, what would you do? And that's not quite answering the deeper question, which is like, how do you come up with them in the first place? But I think it's probably something to think about at the beginning, because it's going to guide a lot of the way that you organize it and think about things, but it's very interesting. And I mean, the other, well, we have, doing some exploratory thing right now, which is like kind of, hopping between, these like game of life type cellular automata things. You have some very low level, model that describes kind of how things evolve. But sometimes you get these sort of emergent phenomena that look like little organisms that walk, and, they can run into each other and collide or do something, and if you wanted to try to figure out, how, the long time behavior of one of these things, like, and then maybe, and there might be interactions, like, if you know that you make a little walker and it's moving along, like at some point you don't need to resolve all these details. You just zoom along until it looks like they're going to collide, right? Mm-hmm. But there's this interesting part where you kind of hop up and down between, like once they go collide, then you need to drop into the low level picture to like exactly how are they hitting, and model that, and then so that ability, like the fact that we're even having this conversation, right? Right. Like I just in very few words explained something that's in my mind, and you kind of know what I'm saying, maybe, I don't know, like, but this jumping back and forth between the levels, it's
right.
So it seems very important to me. It seems very, very important. And how you do that is a good question. So I think, one part is just to start with them and then see how you use them. And then maybe that gives them some guidance.
Yeah, I guess like another example I think of is, suppose I go to work and I put in my bag a flask or a water bottle. I don't need to reason about all the fluid dynamics of, the water inside the bottle as I walk to work. But when I get out and I need to actually pour the water into a glass, now I do need to actually reason about this kind of low level dynamics. And so it seems like this flexible ability to jump between different representations or different levels of fidelity seems key. And then prior to that, it's just like, how do we even represent these different levels in a coherent structure?
Yeah.
But also, I mean, isn't this also something about the task of filtering, right? That we are filtering as, when you look at that water bottle and you put it down, somehow you already know the quantum mechanics of, how the plastic molecules are oscillating, or is completely irrelevant. Mm-hmm. And that it's not a level that you need to access information or infer anything from. You're filtering that out somehow, right? And whereas when you pour, you still understand that you don't have to worry about the plastic, but you do need to worry about the water molecules and the equations of fluid mechanics, right? Which you didn't have to before. So I wonder if it's I keep liking to think it's some kind of filtering, but maybe it's not filtering. Maybe filtering isn't the right word for it.
No, I think you're right. Like somehow you need to know what's relevant. It kind of reminds me of this kind of famous philosophical problem called the frame problem. Dan Dennett has a paper on it. It's like, how do you know what's relevant without actually having already known, right? Like how do I know I don't need to use the low level fluid dynamics before, until, without actually using it, right? And so I don't think we have actually any compelling answers to this question.
And this is why I asked, do you think there's something hardwired? I mean, are there forms of innate knowledge that we already have of the world? And, I look at a lot of these experiments that cognitive scientists with, infants do, right? Like infant cognition. Mm-hmm. And they do talk about how we probably have some hardwired notion of, counting, like, so because if you give a little infant like 3 blocks and then you take away 1, they go wham, because they kind of know that there's something has changed, right? But I don't know whether they're going wham because they actually know that the number has gone down or some other attribute, right? I mean, God knows what,
Yeah, it seems like having, some notion of core knowledge is crucial for learning the kinds of things that humans learn. At the same time, it does seem like we do have a certain amount of flexibility. So going to the point that Kyle just made, like this Zoom, this conversation we're having, but even down to like the Zoom call, right? So how do I use Zoom? I press a button and somehow magically, I get connected. I don't know, like, but underneath that, there's TCP/IP, there's like electrons whizzing around. I don't need to reason about all that to know how to connect a Zoom call, but I might, right? If Zoom stops working, right? And so I don't think Zoom is kind of hard coded natively into my brain or humans' brain, right? But maybe something more abstract, like notions of objects and notions of actions are kind of,
I mean, there's a little bit of chicken and egg stuff going on here too,
right.
Which is, of course, we build these interfaces to fit the things that we know. And,
right.
And also a lot of the examples that we're giving are places where the world does seem to organize itself in this kind of hierarchical way with kind of nice, what's a little bit, when you get into the particle physics side of it, and you see like the separation of scales there, it has like a very, precise mathematical way. And one of the things that's pretty interesting is that, within quantum field theory, there's actually like really deep statements about why the world does separate itself out into these scales. And that's like it's not really clear, it's not obvious at all that you would be able to make such strong statements, but when you then go into things that are like, when you start talking about like society or, some really complex system, it's not really clear that there is any, concise definition. I mean, like a description of the system. I mean, maybe we're just not smart enough to see it, but it's also quite possible that there just isn't some, smaller degree of freedom, reduced description. And if you're in such, if we were kind of like cognizant or conscious at that scale, like that scale of things, maybe we wouldn't be having this discussion, we wouldn't be like presuming things that's actually a useful concept, to like break things down. And I think I'll just say that to me, this is also important. I mentioned in my talk, this kind of no free lunch statement. And I think it's also true when you look at like what's going on with like success in deep learning, is that there's a co-evolution of the architectures of deep learning and convolutional neural networks and things, and the kinds of problems that people were working on, which were, mainly image-like problems at first, right? And then when you go to data that has a very different character to it, those models may or may not, work well, right? And so, and if you really take yourself into the extreme of like any possible kind of data set coming in, so that you really allow yourself like basically totally unstructured looking data, then basically on average everything is equally good or bad, and there's no like magic bullet out there, right? So like so it's important to remember that the extent that any of these things that we're talking about are going to like work or be useful or anything like that is always going to be within the context of some domain of application, and which is also reassuring, because otherwise it's like it is a free lunch, right?
Mm-hmm.
But anyway, so I think it is 5:30, and there is one more question that I would like you, and that's for Kyle from from SBI. The advent of powerful machine learning methods is enabling practitioners to work directly with high-dimensional data and to reduce the reliance on expert-crafted summary statistics. So does the introduction of quantum machine learning or similar techniques or algorithms point to any qualitative rethinking of the above statement?
Well, I'm trying to think. I mean, it seems like, if quantum machine learning or something comes to play, it seems like it would only, either it's going to not be useful or it's going to make it more powerful, right? So I think my statement is basically that previously we really relied on expert knowledge to try to navigate through this complicated data and structure it in a way that we could work with kind of more primitive computational and statistical methods. And when you pair it with machine learning, we can now relieve the pressure on the expert and kind of automate some of that process, which is good. And I think
you can't completely get rid of domain knowledge. You still rely on domain knowledge, right?
Yeah, well, I think that gets into a little bit of a question of, are you just trying to solve this particular task at hand, or are you trying to do the bigger thing? I think, if you really just want the task at hand, pretty surprisingly good at some pretty automated stuff. It's just that if anything goes unexpectedly, or like, you sort of find this, like, what do you do next? If you can't kind of connect what's going on in this automated way back to your domain knowledge, then you don't know what to do. And until we get to the point that we have like much more powerful AI that knows how to generate hypotheses and design experiments and the kinds of things that Zena was discussing, it's important that humans can touch base with that. For quantum machine learning in particular, I think, some of that stuff is a bit speculative. It's, it's exciting, but I think if that stuff works out well, it seems like it's just going to enhance the capabilities of machine learning, and maybe, so yeah, I don't know that it really changes that particular statement, but it certainly will influence the landscape. Yeah.
So any closing thoughts before we wrap up?
I think there's been I appreciate the discussion, and the whole series I think has been pretty interesting. And thank you for having me. Yeah.
Well, thank you so much. Yeah, thank you so much, Zena. Thank you so much, Kyle, for taking the time. And and this was a wonderful sort of in-depth discussion. So I just want to thank everyone for attending, and look forward to seeing you at our next event. Our next event is actually going to be a book talk by Carl Zimmer on his latest book. So that's next week. So I will see you all. Take care and bye. Thanks very much.